50 light-years from Earth, a dead star is slowly turning into a diamond. The name Lucy was not chosen by an international committee or a naming convention. It was chosen informally by the astronomers who discovered what was inside the star. Travis Metcalf's team at the Harvard-Smithsonian Center was working late on the data analysis. Someone in the group started humming the Beatles song, and the name stuck before the paper was. In the formal literature, the object is BPM 37093 from the Bruce Proper Motion Star Catalog. In every popular account since 2004, it has been Lucy, a diamond in the sky made literal. The Beatles wrote the song in 1967, based on a drawing by John Lennon's 4-year-old son. Julian had made a picture of his nursery school classmate, Lucy O'Donnell, floating in the sky. The song had nothing to do with astronomy until astronomers decided it perfectly described their. This kind of informal naming is not unusual in science. It humanizes objects that are otherwise. The tradition goes back at least to the fossil skeleton of an early human ancestor found in Ethiopia. That skeleton was also named Lucy, also after the Beatles song that was playing in the research. The astronomical Lucy and the paleoanthropological Lucy share a name, but nothing else. One is a 3 million-year-old fragment of early human evolution. The other is a dead star. Both carry the same name because human beings find it easier to care about things that have names. Not metaphorically, not approximately, but in the most literal chemical sense possible. The object is called BPM 37093, and astronomers have nicknamed it Lucy. The name comes from the Beatles song, A Diamond in the Sky, taken seriously for once. Lucy sits in the constellation Centaurus, the same constellation that contains our nearest stellar. Alpha Centauri, the triple star system closest to our Sun, is also in Centaurus at 4.37 light-years. Lucy is approximately 12 times farther away than Alpha Centauri, 50 light-years into the Earth. On a clear night in the southern hemisphere, Centaurus is one of the most prominent constellations. The two pointer stars, Alpha and Beta Centauri, are used to locate the Southern Cross. Lucy herself is far too faint to see with the naked eye, and even binoculars cannot reveal her. She appears in professional telescopes as a dim, bluish-white point among thousands of similar. Nothing in her appearance from Earth hints at what is happening in her interior. The crystallization process that is converting her core into the universe's largest diamond produces no visible signature that distinguishes Lucy from any other faint white dwarf in the kid. Only the pulsation frequencies, detectable only with time series photometry over many hours, reveal the internal state that makes her one of the most remarkable objects in our stellar. The universe is full of extraordinary things that look ordinary from a distance. Lucy is a diamond the size of Earth that appears, to any casual observer, as nothing at all. Lucy is a white dwarf, the cooling remnant of a star that burned out long ago. What remains is a sphere of carbon roughly the size of Earth, squeezed to extraordinary density. And at this moment, somewhere inside that sphere, carbon atoms are locking into crystal lattices. The same crystal structure that makes a diamond on Earth is forming inside a dead star. The process has been underway for billions of years and will continue for billions more. By the time it finishes, Lucy will be the largest diamond the universe has ever produced. 10 to the power of 34 carats, a number that requires a moment to absorb. All diamond production in human history amounts to roughly 10 to the power of 9 carats. Lucy outweighs humanity's entire diamond output by a factor of 10 to the power of 25. There's no scale that makes that comparison feel real, which is exactly the point. To understand what Lucy is, you have to understand what a white dwarf actually represents. Stars are not permanent objects. They are nuclear furnaces running on a finite fuel supply. Our Sun converts 600 million tons of hydrogen into helium every single second. That rate has been sustained for 4.5 billion years and will continue for 5 billion. When the hydrogen runs low, the Sun will expand into a red giant, engulfing the inner planets. The outer layers will drift away into space, forming a beautiful, expanding shell of glowing gas. What remains at the center will be the collapsed core, dense, hot, no longer burning. This is a white dwarf, and it is what the vast majority of stars in our galaxy eventually become. Lucy's parent star went through exactly this process some billions of years before our sun formed. The original star burned through its fuel, shed its outer layers, and left behind the core. That core is what we now observe as BPM 37,093, 50 light-years away in the constellation. A white dwarf begins its existence incredibly hot, surface temperatures exceeding 100. It glows white, then yellow, then orange as it cools across timescales that dwarf stellar lifetimes. Lucy's surface currently sits around 12,000 Kelvin, still thousands of degrees hotter than, but it has no internal energy source to replenish what it radiates into the surrounding void. It is simply cooling, the way an ember cools after the fire dies, just on an almost incomprehensible. The interior of a white dwarf is one of the most extreme environments in the observable universe. At the center of Lucy, the density reaches roughly 1 million grams per cubic centimeter. On Earth, water has a density of exactly 1 gram per cubic centimeter at standard conditions. A teaspoon of white dwarf material would weigh approximately 5 tons on Earth's surface. The pressure at the core reaches values that compress matter into states with no terrestrial. Carbon atoms in the interior are not behaving as they would in any laboratory we can construct. The electrons have been stripped from their nuclei entirely, forming a sea of free electrons. The atomic nuclei float in this electron sea, like raisins in an electric ocean. This state of matter is called a degenerate electron gas, and it is what holds white dwarfs up. Ordinary matter is supported by thermal pressure, heat pushing outward against gravity's pull. A degenerate electron gas is supported by quantum mechanical pressure, the Pauli exclusion. No two electrons can occupy the same quantum state simultaneously, and this creates a pressure. This pressure does not depend on temperature at all. It exists regardless of how cold the object. A white dwarf could cool to absolute zero and remain exactly the same size, supported by quantum. This is why white dwarfs do not collapse further under their own gravity. Quantum physics holds. And this is why the crystallization of Lucy's interior is possible in the first place. When the interior cools sufficiently, the carbon nuclei lose enough thermal energy to settle into, instead of floating randomly through the electron sea, they begin arranging themselves into the same repeating geometric pattern that makes diamond the hardest natural substance on Earth. The key question is at what temperature this crystallization occurs inside a real white dwarf. The answer depends on the density and the composition, but for Lucy's interior, it falls around 10. 10 million degrees sounds impossibly hot for crystallization, but density changes everything. At white dwarf pressures, the carbon nuclei are so close together and moving so slowly relative that the conditions for crystal formation exist at temperatures that would vaporize any terrestrial. The crystallization does not happen all at once, spreading simultaneously through the entire. It begins at the center, where density is highest and temperatures have dropped furthest relative to. A seed crystal forms, then grows outward over billions of years as the star continues cooling. The crystallization front moves outward slowly, claiming more of the interior year by year. This is not a process that produces a flawless gemstone in any aesthetic sense. The diamond forming inside Lucy is under pressures that would shatter any crystal we could examine. It is threaded with impurities, stressed by gravitational gradients, and compressed beyond but its atomic structure, carbon atoms locked in a repeating tetrahedral lattice, is unmistakably the same geometry that gives a polished stone its hardness and its particular way of refracting. How do astronomers know any of this is happening inside a star they cannot directly observe? The answer lies in a technique called seismology, and it is one of the most elegant tools. Stars are not perfectly still objects. They oscillate, pulsate, ring like bells struck by internal. Different oscillation modes penetrate to different depths inside the star, carrying information. By analyzing the frequencies and patterns of these oscillations, astronomers can model the interior. The technique is the same principle used in terrestrial seismology to map Earth's interior. Earthquakes produce seismic waves that travel through the planet, revealing layers and densities. Stellar oscillations travel through a star, revealing temperature gradients, composition. A crystallized region inside a white dwarf changes the oscillation frequencies in specific. The stiffness of a crystal transmits vibrations differently than a liquid or a gas under the same. The discovery of Lucy's crystallization came during a period when white dwarf science. For most of the 20th century, white dwarfs were observed primarily as faint points of light. Their spectra revealed surface temperatures and compositions, but the interior was inaccessible. Theoretical models predicted the interior structure, degeneracy pressure, crystallization, cooling, but models are not observations, and the interior of a white dwarf cannot be directly sampled. The development of time series photometry, measuring rapid brightness changes with high precision, revealed that some white dwarfs pulsate in ways detectable from light years away. These pulsating white dwarfs are a subclass called DAV stars, or ZZ Ceti variables. They pulsate because their outer layers enter a partial ionization zone that drives oscillations. The pulsation periods range from roughly 2 minutes to 25 minutes in typical cases. Each period corresponds to a specific oscillation mode that probes a different depth inside the purse. The pattern of periods is as distinctive as a fingerprint. No two white dwarfs have identical. By modeling which oscillation modes match the observed periods, you reconstruct the internal. This technique had been applied to many white dwarfs before BPM 37093. But Lucy was a special case. Her mass was high enough that crystallization was expected to have begun, based on theoretical. Testing that prediction required a white dwarf massive enough and old enough to have crystallized. Lucy fit both criteria, and her pulsation data was precise enough to extract a crystallization. The 90% result was not the first number tried. It was the number that fit the data best. Travis Metcalf at the Harvard-Smithsonian Center for Astrophysics led the team that analyzed Lucy's. His group measured the pulsation frequencies of BPM 37093 with sufficient precision to model the data indicated that approximately 90% of Lucy's carbon core has already crystallized. 9/10 of a stellar interior that was once a nuclear furnace is now a diamond lattice. The remaining 10% near the surface is still in a fluid state, still slowly joining the road. This result, published in 2004, confirmed what theoretical models had long predicted would happen. White dwarfs should crystallize. The physics demanded it, but Lucy was the first direct. It transformed the theoretical prediction into a confirmed fact about an actual object in our stellar. The mass of Lucy places her in a specific context that requires some additional numbers too. She contains approximately 1.1 times the mass of our Sun, compressed into a sphere, roughly. The diameter of the crystallized core is estimated at approximately 4,000 kilometers. That is slightly larger than the distance from New York to London, packed with crystallized carbon. The total mass of crystallized material translates to 10 to the power of 27 tons of point. Written differently, 1 billion tons of the hardest natural substance. The entire history of human diamond mining has produced approximately 500 million carats. Each carat is 0.2 of a gram. The total human output is roughly 100,000. Lucy's crystallized core masses more than all human diamond production by a factor so large that it requires scientific notation to write down, and even then, the number lacks intuitive. The distance of 50 light-years places Lucy in what astronomers call our stellar neighborhood. Light, traveling at 300,000 kilometers per second, takes 50 years to cross that. Our fastest spacecraft, the Voyager probes, travel at roughly 17 kilometers per second. At Voyager speeds, reaching Lucy would require approximately 800,000 years of travel. Lucy is our neighbor in the way that the nearest town might be your neighbor in an infinite desert. Technically close, practically unreachable by any technology we could build within human timescales. But the distance matters less for understanding Lucy than what it tells us about stellar. If there is a crystallizing white dwarf at 50 light-years, there are many more at greater. The Milky Way contains an estimated 10 billion white dwarfs, representing the remnants of dead. Many of them are old enough and cool enough to have undergone full or partial crystallization. The universe is already full of diamond stars, cooling and crystallizing in darkness across the age. We simply had not confirmed the process observationally until Lucy gave us the data to do so. The physics that governs Lucy's crystallization also governs the future of our own solar system. The sun will exhaust its hydrogen fuel in approximately 5 billion years from this moment. The timeline feels abstract until you compare it to the age of the Earth, which is 4.5. The Sun is roughly halfway through its main sequence life, and its second half has already begun. When the hydrogen fuel runs low, the Sun's core will contract, and its outer layers will expand. Mercury, Venus, and probably Earth will be engulfed as the Sun swells into a red giant. The expansion phase lasts only a few hundred million years, brief by stellar standards. Then the outer layers drift away as a planetary nebula, and the core contracts to a white dwarf. The Sun will leave behind a white dwarf with a mass of approximately 0.6 solar masses. That remnant will be roughly the size of Earth, dense beyond imagination and slowly cooling. The cooling timescale for a white dwarf to drop to room temperature exceeds 10 to the power of, that number, a quadrillion years, is 100,000 times the current age of the universe. The universe itself will have changed beyond recognition before our Sun's remnant finishes cooling. All the galaxies we observe will have long since used up their star-forming gas and gone dark. The last red dwarf stars, the most miserly consumers of fuel, will have exhausted themselves, and black holes will have swallowed most of the mass in the universe, themselves slowly evaporating. In that almost unimaginably distant future, the cooling white dwarf remnant of our Sun will still radiating its residual heat slowly into the dark, still supported by quantum mechanical. And at some point in that timescale, its core will have cooled enough to begin crystallizing. The carbon and oxygen at the center of our Sun's remnant will begin to lock into diamond lattice. The same process happening inside Lucy right now will happen inside our own dead Sun. 50 light-years away, we can observe the future of the object currently giving us life. Lucy is not just a curiosity. She is a time machine pointed at our own stellar fate. The crystallization process raises a question that planetary scientists have explored with some. What happens to any surviving planets or moons when their host star becomes a white dwarf? The outer planets of our solar system, Jupiter, Saturn, Uranus, Neptune, will survive the red. They will not be engulfed, though their surfaces will be dramatically altered by the increased. After the Sun sheds its outer layers, these planets will find themselves orbiting a tiny, cooling. The solar luminosity will drop precipitously, and the surviving planets will freeze to their cores. Whatever life might have colonized the outer solar system would face an environment hostile beyond. But the planets themselves will persist, orbiting a dead star for as long as the Sun's remnant. The same will be true around Lucy, if her parent star had outer planets that survived its death. Those planets, if they exist, are orbiting a crystallizing diamond in perpetual darkness 50. There is a different kind of question that emerges from the physics of Lucy's crystallization. The latent heat released when a crystal forms has to go somewhere, and inside a white dwarf, it does. As the carbon lattice solidifies, it releases energy that temporarily slows the cooling of the star. Crystallization actually keeps white dwarfs warmer for longer than they would otherwise be. This effect was theoretically predicted decades before it was observationally confirmed in white. When astronomers counted white dwarfs at various temperatures, they found a surprising excess of clustered around the temperature range where crystallization was expected to be releasing latent. The stars pile up at that temperature because they cool more slowly as they solidify. It is as if the stellar remnant briefly resists its own death, burning a little hotter before the... In 2019, a team analyzing data from the Gaia Space Telescope confirmed this crystallization pileup. Pierre-Emmanuel Tremblay at the University of Warwick led the analysis of 15,000 white. The data showed a clear excess of stars at the colors and luminosities where crystallization occurs. The universe was piling up diamond stars at a specific cosmic temperature, exactly as physics. That Gaia result transformed the crystallization of white dwarfs from a known process to a measured. It gave astronomers a new tool, the pileup, for estimating the ages of white dwarf populations. Stars that form together in a cluster will have white dwarf remnants at roughly similar. By finding where the pileup falls in a cluster's white dwarf sequence, you can date the cluster. The white dwarfs in our galaxy span ages, covering the entire history of stellar evolution here. The youngest white dwarfs formed from the most massive stars, which exhaust their fuel quickly. Massive stars burn so intensely that they die in millions of years rather than billions. Their remnants can become unusually massive white dwarfs near the Chandrasekhar limit. The oldest white dwarfs formed from the first low-mass stars to die in the Milky Way's history. Those ancient stars lived for billions of years before their remnants entered the cooling sequence. The coolest and faintest white dwarfs we observe today are the oldest, stellar fossils. Measuring the temperature distribution of white dwarfs in a cluster reveals when those stars formed. White dwarf cooling age dating is one of the primary tools astronomers use to measure stellar ages. The crystallization pileup discovered in Gaia data adds a new layer of precision to this technique. When crystallization occurs, latent heat release slows cooling and creates a demographic excess. White dwarfs pile up in temperature at that moment the way traffic piles up at a slow road section. The location of the pileup encodes the mass and composition of the crystallizing population. By finding the pileup in a cluster of known age, astronomers calibrate their cooling models. By finding it in field populations, they reconstruct the history of star formation in the Milky Way. Lucy's physics is not just the story of one dead star. It is encoded in the lives of billions. Understanding crystallization means understanding the stellar graveyard of our neighborhood. The physics of Lucy's interior is therefore not just an exotic curiosity about a nearby dead star. It is a precision tool for measuring the history of star formation across billions of years. The diamond inside Lucy encodes information about the age of stellar populations we cannot otherwise. The extreme conditions inside Lucy produce a type of matter that has no earthly equivalent in scale. Diamonds on Earth form deep in the lithosphere, typically at depths between 1 and 300. The pressure there reaches roughly 50 to 60 kilobars, 50 to 60,000 times. Inside Lucy, the pressure at the center exceeds this by a factor of hundreds of millions. The diamond forming inside a white dwarf is not the same material as what comes from Earth's mantle. It is a more extreme form, compressed beyond anything our laboratories can produce or study. The crystal structure may be modified by the enormous pressure into phases that have no terrestrial. Carbon at extreme pressures can adopt structures other than the standard diamond cubic crystal. These high-pressure phases, called diamond 2, post-diamond, or metallic carbon and various, may exist in portions of Lucy's core where the pressure exceeds what standard diamond can sustain. The boundary between ordinary crystallized diamond and these more exotic phases is not precisely. Mapping it would require laboratory pressures we cannot yet achieve and sustain for meaningful. Lucy's interior is therefore also a natural experiment in extreme material science beyond our reach. A laboratory the size of Earth, operating at conditions we can model but never replicate. Travis Metcalf, who first confirmed Lucy's crystallization through seismology, made an that has become one of the more quoted lines in the popular accounts of this discovery. He noted that when we look at Lucy, we are looking at the future of our own sun, not a possible future or a likely future, the definite future, written in the physics of stellar. The sun will become a white dwarf. That white dwarf will crystallize. The crystallized remnant will. These are not predictions in the sense of uncertain forecasts. They are consequences of established. The only uncertainty is in the precise timescales and the details of what survives the day. Every diamond on Earth began its existence under pressure and heat in the mantle, then was carried. The carbon that forms those diamonds was itself forged in the cores of stars that died before our. Carbon is not a primordial element. It was not produced in the Big Bang like hydrogen and helium. It was synthesized in stellar interiors through the triple alpha process, 3 helium nuclei fusing. Every carbon atom in every diamond ever mined on Earth was created in the nuclear furnace of a dead. The diamond industry is built on the remnants of stellar processes that concluded before Earth. Lucy is simply the most extreme version of a process that connects stars, planets, and gemstones. The carbon in her core came from nuclear fusion. The fusion happened in a star. The star died. The carbon in your body followed the same path, forged in stars, scattered in supernovae, assembled. Lucy's not a strange outlier in the universe. She's an illustration of how the universe processes. Stars forge elements, die, scatter them, and the remnants slowly crystallize into the most ordered. The universe is not becoming more disordered on stellar timescales. It is building diamonds in them. In the year 2004, when the Harvard team published their astro-seismology results, confirming the discovery was framed in terms of the Beatles song, and the diamond metaphor was played for. The actual scientific significance was somewhat more subdued in the technical literature than in the confirming that white dwarfs crystallize was important, but theorists had expected it for decades. The observation confirmed the theory. The theory was not overturned. This is science. What made Lucy genuinely interesting to theorists was the precision of the measurement. 90% crystallization was a specific, quantitative result that could be compared to models. The models predicted when crystallization begins based on white dwarf mass, composition, and age. Getting a real number from a real star allowed theorists to test the equation of state of dense. The equation of state describes how matter behaves at extreme pressures. It is the foundational. Matching model predictions to Lucy's 90% figure validated the theoretical framework. Future astroseismology measurements of white dwarfs at various temperatures will refine it further. The Kepler Space Telescope, primarily designed to find exoplanets, also observed pulsating white. Its data provided astroseismology measurements of unprecedented precision for stars other than the TESS mission, Kepler's successor, continues this program of measuring stellar oscillations from each additional white dwarf characterized adds another data point to the crystallization physics. Eventually, this data will constrain the equations of state well enough to model Lucy's interior. The diamond star 50 light-years away is a calibration target for the physics of matter under. There is a philosophical dimension to Lucy that the scientific papers do not address, but cannot. The sun is alive in the sense that it is actively processing fuel and releasing energy. In 5 billion years, it will die, in the sense that the fuel will run out and the furnace will go. The white dwarf remnant will cool. The cooling will take longer than anything else in the observable. At some distant point, the crystallization will complete and the cooling will continue toward. The remnant of our star will exist as a dark, cold, crystallized diamond sphere in empty space. Astronomers call the hypothetical completely cooled white dwarf a black dwarf, though none yet. The universe is not old enough for any white dwarf to have cooled to the point of invisibility. Every white dwarf that has ever formed is still warm enough to emit at least some detectable. Lucy herself will not reach the black dwarf stage for an almost incomprehensible period of time. But the trajectory is set, the physics is clear, and the destination is a dark diamond in the. Whether that constitutes a kind of immortality or simply a different mode of existence is not a cup. The carbon that forms Lucy's diamond was processed through nuclear fusion, released in a stellar, and is now crystallizing into the most durable structure that chemistry allows under any pressure. It will remain that structure until something external disrupts it, and nothing is likely to. And the diamond inside Lucy may be the most permanent object within 50 light-years of Earth, more permanent than the planets, more durable than the stars, outlasting everything else in a crystal of pure carbon, slowly growing in the dark, 50 light-years from the planet where we. The question of what the sun's white dwarf remnant will look like in 5 billion years has a. Current models predict a mass of approximately 0.54 solar masses for the suns. That mass would produce a white dwarf roughly the size of Earth, slightly smaller than our planet. The surface temperature immediately after formation would exceed 100,000 Kelvin. Over the first billion years of cooling, the temperature would drop to something resembling Lucy's. By the time it reached Lucy's current temperature of 12,000 Kelvin, crystallization would. The timeline from formation to substantial crystallization depends on the exact cooling rate of that. Models suggest it would take several billion years of cooling before significant crystallization. By then, the universe would be roughly 25 billion years old, nearly twice its current age. No living thing related to what exists on Earth today could plausibly survive to observe that. But the physics guarantees it will happen, regardless of whether anyone is watching. The sun's carbon will crystallize. The crystal will be diamond. The diamond will cool, and eventually, What happens after that is constrained only by the cosmological timeline of the universe itself. In a universe headed toward maximum entropy and heat death, the sun's remnant will persist as a cold. Lucy shows us that remnant in progress, our own future written in the physics of a nearby dead. The question of whether any life could detect Lucy's crystallization from her own vicinity is one of those thought experiments that physics permits, but practicality makes nearly impossible. Lucy has no known planets. Her parent star's planetary system likely did not survive stellar death. The extreme environment of stellar evolution typically scatters or destroys interplanetary systems. But distant outer planets could in principle survive if they were far enough from the dying star. Whatever orbits Lucy, if anything does, exists in perpetual darkness 50 light-years from our sun. The light Lucy emits is a pale fraction of what a living star produces, faint thermal radiation. Any hypothetical observers nearby would see an object far dimmer than our sun appears from Earth. At planetary distances from Lucy, there is no warmth, only the coldness of interstellar space. They would not know without instruments that their dead star was slowly crystallizing into diamond. The fact that Lucy is crystallizing is knowable only through pulsation frequencies we measure here. The universe contains wonders accessible only through specific measurements at specific moments. Lucy's crystallization was knowable in principle the moment humans first understood stellar physics. It became known in practice only when the right telescope, technique, and team converged on it. Every discovery in astronomy is knowable in principle far longer than it is actually known in fact. Knowing it matters not because it changes what Lucy does, but because of what we now understand. The diamond growing inside Lucy grew the same, without our knowledge of it, for billions of years. It will continue growing whether or not anyone on Earth continues to study it going forward. But knowing it places us, briefly and with great effort, inside the physics of a dead star. That placement is what science exists to achieve, and what curiosity has always been the engine of. The Sun is 4.5 billion years old, and roughly halfway through its main sequence life. Its core is now about 1.5 times as hot as it was when it first ignited long ago. Over 5 billion years, the luminosity will increase by roughly 10% per billion years. Earth's oceans will begin evaporating within 1 billion years as the sun continues brightening. This is the moist greenhouse effect. Water vapor accumulates and accelerates atmospheric warming. The surface of Earth will become uninhabitable long before the sun actually becomes a red giant. Whatever life exists at that point will have moved or adapted beyond anything we can envision today. The red giant phase begins when core hydrogen is exhausted and the outer layers start expanding. The sun will swell to roughly 200 times its current diameter over millions of years. Mercury and Venus will be engulfed entirely. Earth's fate depends on the timing of mass loss. The expansion phase lasts roughly 500 million years before the outer layers drift away. That is brief by stellar standards, but longer than all of complex life's history on Earth. The planetary nebula phase that follows is one of the most beautiful structures in astronomy. A glowing shell of expelled gas lit by the hot remnant, visible for tens of thousands of years. The Helix Nebula in Aquarius, 650 light-years away, shows what our sun will produce. Its fading remnant glows at the center, just as the Helix's central star glows in our sky today. Every planetary nebula we can see is a preview of what our sun will eventually produce and become. Then the nebula disperses, the star cools, and the long, slow cooling of the white dwarf begins. The sun's remnant will radiate stored heat for billions of years after the nebula dissolves. Lucy shows us this process already underway in a star that completed it long before our sun formed. The 50 light-years between Lucy and Earth is also a time gap of several billion years of cooling. Lucy's parent star died and cooled across a timescale that spans all of Earth's biological past. Watching Lucy is watching a process our own star will complete in a future equally vast and certain. We have a nearby example of our own stellar fate available to study at exactly this moment in time. We evolved the capacity to understand stellar physics when a nearby dead star could teach us. Whether that timing is meaningful or coincidental is a question physics cannot address. The diamond cooling 50 light-years away does not know it is being observed from across the void. The crystallization does not pause to be measured or hasten to be dramatic for any audience. It simply proceeds, carbon atom by carbon atom, at whatever rate the internal physics allows it. That indifference is part of what makes it striking when observation finally manages to reveal it. The universe does not arrange itself for human benefit, but sometimes the arrangement is convenient. A crystallizing diamond star, 50 light-years away, visible to the instruments we built right now. The discovery required quantum mechanics, stellar theory, and one team willing to run the numbers. The number they arrived at, 90% crystallized, is a statement about an atomic lattice. It is a statement about the sun's future, the fate of Earth's carbon, and the destiny of matter. A teaspoon of white dwarf material weighs 5 tons. A crystal of it covers the volume of Earth. Science reaches from subatomic to cosmic scales, and Lucy somehow spans both ends simultaneously. Her crystal lattice has the same atomic spacing as any diamond ever worn on any finger on Earth. Her total mass exceeds all of humanity's diamond output by a factor requiring scientific notation. The universe operates on scales that only mathematics can bridge, and only patience can appreciate. Lucy has been crystallizing for longer than the Earth has existed as a recognizable planetary body. She will keep crystallizing for longer than Earth will remain in any recognizably habitable form. When finished, she cools in darkness for timescales that make the universe's current age seem brief. In that entire arc from the nuclear fires of her parent star to the cold crystal at her endpoint, she will have converted stellar mass hydrogen into stellar mass diamond through pure patience. That is what is happening 50 light-years away, at this moment, in the direction of Centaurus. A dead star is slowly becoming a diamond, in the most literal and verifiable sense possible. Thank you for following this journey through the death and crystallization of a nearby star. If this story moved you, subscribe and stay for the next chapter of the universe's slow. Your curiosity about what happens when stars die is what keeps the strangest science alive.